What's up, guys? Welcome to today's show. So today we're gonna do something really exciting. We're gonna create our own file system in code. So this will be a very interesting endeavor, and let's begin very soon. First, I'm just gonna show you a little plan that I've made for the different functions. I'm going to start with the formatting and the show function, which will display a couple of informational bits about the file system, like the different inodes and info about the superblock and such things. Then we need to be able to mount and unmount the file system. We need to be able to create an inode, and an inode is a low-level file. So every file has an inode, and it's basically a header describing the file or the directory. And this destroy function will remove an inode, and then we will have some functions to load and save it to the disk. A stat function which obtains some information like the file size. We're gonna have a free block bitmap, which is just it's an array of booleans basically, where every 0 means a free block and a 1 is an occupied block. So we'll create a function which creates the bitmap based on scanning the disk, and then this will allocate a new free part of the bitmap, one block, and this will remove one. And then we need to have read and write functions, which might be quite difficult to write, because as you remember, the disk emulator will only read and write 512 byte blocks, so we need to somehow account for that when we read and write smaller parts. And we'll also have something like an open directory and open file, which the first one will return the contents of a directory, so the different files and other directories, and the open file will read in an entire file into the memory. We'll also have a couple of constants, the two magic strings. We will have 16 inodes per inode block, because they are 32 byte in size each. We will have 8 pointers per inode, and these are the direct pointers. And we will have 256 pointers per block when we are talking about indirect ones. Alright, so let's start by setting up our files. I'm gonna create 2 different files. I'm gonna close a couple of these because it's too much to have all of those open. Okay. So let's see. We need to have the disk and the OSApi and the OS. Alright, so let's create a couple of files. First we'll have an fs.c, which will contain all the functions stuff. And this is going to include fs.h, which we will also create. fs.h. And we will only include this once, so let's add that in a pragma. Alright, but I will also create something like, there are different types of std libraries. So we have stdio and we have stdlib, We have uni std and so on and so forth. But we can't use any of those because we're creating an operating system and we will not have access to the standard C library. So I intend to create my own std library, which I will call omni std .c and .h. So this will contain all of these different std things, not the whole libraries, but some of the functions that we need to use. So this will be omni std.c, which in turn will include the omni std.h. And similarly, we will have an omni std.h. And we'll set the pragma ones here as well. Alright, so let's start by updating our make file. So we will have an omni std.o, which depends on omni std.c and omni std.h. And this will be very similar to the other ones that we have. So maybe we can copy this, 2dd paste. So the second one will be our fs.o containing fs.c and fs.h. And when we have those two, we can link them into our library. So omni std.o and fs.o. Okay. So let's see. I need to put all of these tabs in some order so I can find things easily. I think I'm gonna have all the C files to the left. Maybe here. And maybe I should try to keep the same order for those things. So this will be right here. And os.h can be to the right. Alright, so let's start by preparing the header files. So how did we do it in disk.h? Okay, we include those two, so let's do the same. In both this one and in fs.h, like so. Did we begin the .c file in some specific way? No, we just include that, alright. Alright, so creating a file system is quite a big thing. So where do we start? And as I usually say, when in doubt where to start, always start by defining the data structures. So we'll go into our fs.h and we will need some structure for the actual file system. So this will be a, let's see, an internal thing, not private. And it will be packed. It's a struct s file system. And this will contain the drive number. And we need to have a disk descriptor. We need to have the free block bitmap. And I will also keep a copy of the super block. Call this metadata. And perhaps I will have a directory root, but let's wait with that. I'm not sure if I'm going to do it that way. So let's type def this struct s file system, and we'll just call this type file system like so. Let's also define these different types of constants. So we'll have a magic one, which is DDO5. Have a magic 2, which is AA55. And this is so we recognize our file system. We will have, maybe I need a little bit more space. We need an inodes per block. Which will be 16. We need to have pointers per inode. We'll have 8 of those. And we need to define pointers per block. 256. Alright, so that's hopefully all the constants that we need. And I'm going to change one thing from the disk. Or not the disk. What did I think about? The errors. Since I don't need to use 0, 1, 4, and so on and so forth, because there will only be returned one error. We can't have several of those, so we don't need to do it like this. Instead, I'm going to do an anonymous enum. And if you don't know what that is, it is something which looks like this. So it will be a public thing, public packed enum. And it does not have a name. All I will put in here is those errors. And the C compiler will automatically create all of these and assign them numbers. And now we should be able to use these as constants. We do need to move this down somewhat though. There we go. Let's see if it compiles. Yes, it does. Alright, so let's not care about that. By the way, maybe we can do this. Unknown type name disk. Ah, that's right, we haven't defined those. So let's do that. Disk, it should recognize though. Maybe we need to include that specifically. So include disk.h. So now we only need to define the super block. So what is a super block? That is also a struct, right? So this will be an internal packed struct as super block. And let's put everything in here for now. Maybe we can optimize it later on. So let's start with the boot sector. Let's do int 8. Boot sector. And these are 500 bytes. Then we have 2 reserved bytes. So int 16, I will just do this. Then we have the number of blocks, so int 16 blocks. We have the number of inode blocks, int 16 inode blocks. We have the number of inodes, also in int 16. And then we have the 2 magic strings. So we can do int 16 magic 1, int 16 magic 2. And maybe you wonder why I include like the reserved field and the boot sector and these magic things. Will we ever use that? Well, I want to put everything in here because then we can just fill this in and write that to the first block, which makes the formatting a little bit easier. So let's do a type def struct as superblock like so. And now I think it will compile. Yes, it does. Okay. So what's the next thing we need to do? Well, we need to define an inode as well. It's a lot of data structures. So this will also be an internal packed struct as inode. And what does an inode contain? Well, first of all, we have the valid and type fields. So let's see how we're gonna do that. Maybe we can do a substruct, which I will call valid type. So the first 4 bit, and this should also be packed by the way. So the first 4 bits are reserved. So let's just do int 8 like so, and 4 bits. The next 3 bits are the type field. So maybe bool. Or let's do this. So this is the type, which are 3 bits. And we will also have a bool for the valid 1 bit. Then we will have the size in bytes. We will have the file name. And this will be its own data structure. So file name, name. Then we have the indirect pointer. So maybe we can have a type for that as well. So pointer indirect. And then we have the direct pointers. So this will be a pointer. Indirect. And here we will make use of our definitions. So pointers per block. No, this is pointer per inode. Pointer per inode, like so. And this is the entire structure. So we'll type def struct s inode as inode. And we need to define the file name and the pointers. Let's start with the file name, which will also be an internal packed struct s file name. And why not a string? Well, I want to divide this with the file name and the extension. So this will be an int 8 name of 8 bytes. And then we will have the extension 3 bytes. This will be our file name type. And then we need to have the pointers. We'll define those up here. So first I will define a pointer. Yeah, because there are 2 different kinds. So let's say we have an inode pointer. And this will simply be a block number. Or actually it's going to be an inode number. And we need to have a block pointer. let's use this as inode pointer, and this will be a block pointer. I do also want to have some kind of structure because a data block can be any number of things. It can be a super block, but it can also be an actual data block, or a block full of pointers and so on and so forth. So maybe we can create let me just check one thing. A union is what I was thinking about. So a union is similar to a struct, but it will only contain, a struct contains all of these, for instance. If this were a union, it would only contain, either this, or this, or this. So one thing at the same time, so to speak. So let's say we have an internal packed union, and let's call this an fs block. So ufs block. So it's either a super block or it's a data block. Let's say it's an int8 data block size. Or it's a block full of pointers. And it can be either inode pointers or block pointers. Maybe we should only have one pointer type. Yes, I think so. So let's just do type def int16 pointer. So we will have pointer, and these are pointers. And this will be pointers per block. So what else can it be? I thought it was going to be 3 different things. Super block. Well, it can be an inode block as well. So these will be inodes, and inodes per block. So let's do type def union fs block, and this will be fs. Let's do it like this, or maybe like this. Okay, so now we have our data structures. Now we can start implementing this plan of functions. And I'm going to start with the format because that should be pretty easy. And I have selected this order based on my own thoughts of what's going to be easy and what's going to be hard, perhaps. But also some ideas from the SimpleFS file system and their order. So I think this is going to be fine. So what will be the signature of the formatting function? Well, it's going to return true or false if it succeeds, so boolean. It's going to be called fs format. And it needs to take in a disk. And maybe this can return the file system instead. So we need the disk. Do we need anything else? Well, we need to know if we're going to write the boot sector or not. So we need to actually provide the boot sector, which means we need to create a type for that, type def, and this will be int8 boot sector 500. So let's change this to boot sector boot. Let's make this a pointer. Anything else? No, I think this is enough. Let's copy some stuff. So the copy function and the zero function should be inside of the OmniSTD instead. And same with the .c stuff. So we'll take this zero function, put here, and then we have the copy function. And I do also want to have some string copy function. And it will be very similar to this. So maybe we can rename this memory copy. And then we make a definition. So the copy of destination, source, and length will be memory copy of destination, source, length, and true. No, false. And what is this false? This will be a Boolean string. So is this a string or not? So let's do this. So if string is true, and the current position of the source pointer is equal to 0. So if we run into a 0 byte, we want to break. Otherwise, we can just do this. So that's the only difference. So now we can also define a string copy of DSN, which will be a memory copy of DSN true. We'll take those two and move them into this. And this we change to memory copy, and we add the Boolean. Alright, will this thing still compile? That is the question. Packed attribute ignored for struct anonymous. Duplicate member indirect. Really? Yes. This should be direct instead. And let's save those files. I need to include that file. So OSAPI.c. And same with the disk. And let's fix this too. So 46. And does the command still work? Yes, it does. And now we have a little bit better structure. So let's see. And in our init function, we need to assert that we haven't already initialized. No, that's not really necessary. However, when we attach, what was I thinking about? Attach, detach. Never mind. All right, so let's do the formatting function. Let me just remind myself about the signature. So it will return file system, fs format, disk, boot sector. Okay. So file system, fs format, and this would be, should this be public? Let's see. Maybe. Let's make it internal for now and we can fix that later. It's going to take in a disk descriptor and it's going to take in a boot sector. And MBR is short for master boot record. So we're going to need a file system fs. Gonna need a size. Gonna need inode blocks. How many? We need to keep track of the number of blocks as well. Right. So let's begin by checking that we really have a disk mounted or attached. So if we don't, we will return an error immediately. File system *0. Maybe we should indicate an error here. Let's go here and we need an error not attached. Alright. So let's start by creating this structure of the super block. So super block, super. And we will also need one inode, because when we format, we will create one inode, which is inode number 1, the root directory. By the way, I think I'm going to change one thing. I don't want to overcomplicate this here. So let's just do int8 valid type. And then I will create another anonymous enum. So we'll have a type not valid, which is 0. We'll have a type file, which is 1, and a type directory, which is 3. That's what I want. Maybe IDX. So inode is short for index node, that's why I named it like this. Alright, so let's start by figuring out how many blocks it's going to be. That's simple because we can just take it from the DD. Then we need to figure out how many of those blocks should be inode blocks. So inode blocks should be equal to number of blocks divided by 10. So 10% should be inode blocks, but we need to round this upwards. So if blocks mod 10 is not equal to 0, that means we have a little bit more than 10%. So let's do inode blocks plus plus. So let's set up our first inode. Valid type field should be a directory. So type directory. Size in bytes should be 0. File name should be 0. File name should be all zeros. I think either that or we'll set it to something which is not a valid file name otherwise. But let's do this for now. And then we don't really need any pointers or indirect pointers. So IDX indirect is 0. Let's calculate size of pointer. So how big one pointer is times pointers per inode. And we will zero out the index direct with this size. Okay, so now we have created everything we need for the first inode. Now we need to create a super block. So let's start from the last parts of it. Magic 2 should be magic 2. Magic 1 should be magic 1. That's simple enough. Then we have the total number of inodes. That's 1. The total number of inode blocks. That's inode blocks. And the total number of blocks is just blocks. And the reserved field is just 0. So now we need to copy the boot sector. So let's do if we have a boot sector, then we copy into the super boot. We copy the boot sector and the size 500. If we don't have a boot sector, then we do a 0 of it instead. 500. Okay, so now we have everything that we need. So now we want to do the actual write. By the way, I want to do one more check. Let's say we have a function which returns all the open files, or number of open files on a file system. So open files of dd so if this is a positive amount, by the way, let's add a force boolean. So if we have current open files, and if we don't do force, then we return an error of what should we call this? Busy. But if we don't have any open files on the disk, or we use the force, then it goes through anyway. But if we do use the force, by the way, maybe we should do this. So if we use the force, then we want to make sure that we close all open files. So close all files of dd. Something like that. Alright, so how do we write this to disk in an easy enough kind of way? Let's create a boolean for if it's okay or not. So okay is true for now. So let's start by writing the super block. So we will do a disk write, and this takes in a disk descriptor and an address to read the data from, and that will be the address of the super block. And which block are we going to write? This is the first block. And our OK will be equal to this. We'll return an IO error if it doesn't work. And now we need to write the inode blocks. And we actually only need to write the first because the rest can be 0, I suppose. Yes. So OK will be equal to d write dd, and this will be the index block number 2. And I guess that's it. Maybe we need to zero out the inode blocks, at least. So it doesn't contain old information, which messes with our stuff. I think that's good enough. At least we need to set the valid type field to 0. So let's define an n. So for n is equal to 0, as long as n is less than inode blocks, n plus plus. let's do this. Let's zero out or maybe we could do something like this. We'll create an fs block, fsb. Let's zero the fsb block size. And for each inode blocks, we want to set OK equal to dwrite dd fsb. And what's the block number? Well, it will be 3 and onwards, right? So n plus 3. And if it's not okay, return an error of IO. Okay, I think that is good enough. Now we just need to return a file system. So the size is going to be equal to the size of struct as file system. So fs will be equal to malloc of that size, and we are going to zero out this fs of size, and now we need to set the different parameters. So fs drive is going to be dd drive, fs dd is going to be dd, then we need the bitmap. Let's for now do bitmap equals bitmap. And we'll store a copy of the superblock, so let's copy this to fs metadata. And we'll copy from super block size. that's basically it. And we can return this file system. Alright, so we need to create this bitmap. So I have these three functions. Maybe we should make these now. So we will have an internal constructor function which is going to return a bitmap. And how did we define this bitmap? As a pointer to a number of booleans. So internal bool make bitmap. And this is going to take a disk descriptor and maybe a boolean that says if it's gonna scan the disk or not. Then we need an allocation, which will return a block number. So bitmap alloc. And I don't think we need to have any arguments to this, because we just want to find the first possible one. But we are going to allocate that. I think we need its own type anyway. So bitmap star. This is going to return a bitmap star. We will also have a void bitmap free, which takes in the block number and the bitmap. Alright, so let's create these functions. So internal bitmap make bitmap, and we need to have a disk descriptor and a boolean if this is going to scan or not. So we will have a bitmap bm in 16 size. If we don't have a disk, we can return an error. So we're going to have 1 bit per block, which means the size is going to be the number of blocks on the drive divided by 8, I guess. So if dd blocks mod 8, so if we have a carry, we will increase this by 1. bm is equal to bitmap malloc. By the way, we should use the alloc name, not the malloc. And this will be the size. Because I think I did a macro for that. Yes, alloc is malloc, but it should be changing this to an integer as well. Because alloc is my own mallocing function, which is not fully developed yet, but will be pretty soon, so I want to be able to switch easily. And let's, by the way, check that we have a BM, and if not, we return an error. Well, we don't need to specify. I will only specify the error type on the public functions. Let's do the same here. Look. We need to have an error type for this when the mallocing fails. So let's call it error no memory, or just memory perhaps. No memory. Alright. So if we are not going to scan the disk, what should the bitmap be? Well, all zeros, I guess. So in that case, we can just return BM. And we need to zero it out. So BM size. But if we're gonna scan the disk, how do we do this? Well, we need to have a loop. So for n is equal to 1 is the first block. We're going to loop as long as n is less than or equal to the dd blocks n plus plus. And for each block, if well, we need to read in that block. Let's start by zeroing out our structure. So ret is equal to disk read, and we take the dd and we take the address of the block, and the block number is n. And if ret is false, then we can return an error, but we need to free this as well, so we shouldn't use free, we should call it destroy. And this is our bm. And then we return bitmap star false. So otherwise we have this block. Let's also create an index, so int16 index. Let's also do bool valid. And valid should be equal to this block. Let's see. We don't need to go through every block. We need to go through the inodes. That's what matters. Maybe we should take in the file system instead for the disk. Alright, so then we want to scan the inode blocks. So the first actual block is going to be block number 2. And as long as n is less than or equal to the inode blocks. So if we have one inode blocks, we're gonna scan block number 2. So the number of inode blocks plus 1, right? So if we have 1, so I think this is right. Alright, so we read in this. And then we will have inodes. Inode, inodes, inodes per block. And the index is equal to will we have an inode 0 or will it start at 1? I think we're gonna have an inode 0. So the index is n at this point. The index of the inode blocks. So we need to have an additional for loop. So for x is equal to 0, as long as x is less than inodes per block x plus plus. So now we're at the actual inodes, and the valid field will be this inode. So how did we do it inside of fs.h? We have, okay, so the fs block is one of these. So we can access the inodes. So we don't need this. So we go into the block dot inodes at this index. And we grab the valid type field. And we need to take the last bit, which means we will AND this with 1. And let's set index to 0. And if this is valid, then we will set the bit, what do we call it, BM. BM at the BM at the index should be equal to true. Otherwise, BM at the index should be equal to false. And then we increase that index. And this we do for every inode of this block, and we go through every inode blocks as well. Okay. And now we should just be able to return that bitmap. Alright, a little bit messy function. I hope it's going to work. And what else? We need a bit. Let's update the signature. So instead of a disk, we take in an file system star. Alright, so the next function we need is the allocation function. So this is going to return a block number. And this is bitmap alloc. And the signature, well, it just takes in the bitmap. So it will allocate the first free bit, basically. Bitmap BM. So we'll have an int 16. Well, we do need to pass the file system as well. So in int 16n, do a for loop where we set n equal to 0. And we go as long as n is less than or equal to fs fsdd blocks. And this time we only need this and n plus plus. So if the bitmap at I is equal to 0, then we'll set the bitmap at I equal to true. Let's do one, by the way. Or let's do it like this. So we'll set this to true, and we'll set the block number that we are going to return equal to I plus 1, n plus 1. And we return BL. But if we go through this entire loop without early returning, then we will return 0. And same if we don't have bitmap, we'll also return 0. And if we don't have a file system, same thing. Right, that's simple enough. And the other one will be pretty simple as well. This is bitmap free, and this is a void, I think. Yes, file system bitmap block. File system bitmap block. And here we don't need to scan anything. We'll set n equal to the block -1. And we'll set the bitmap of that index equal to false. And that's all. Okay, so now that this is done, we can set this bitmap equal to make bitmap. We give it the fs, and we're not going to scan. But we are going to allocate a specific bit. So the only thing well, let's see, how many blocks are we using? We are using the super block, the inode blocks, and one directory. Let's do this. Bitmap bm. So let's this be equal to bm, but first we need to create that. So bm is equal to make bitmap of fs and false. And we will we can reuse the size variable. So the size is going to be equal to 1, which is the super block, and then 1, which is the directory root, plus the dd, the fs, where is it? Let's see, it's inside of fs, super, fs metadata, inode blocks. So these are how many we are going to set. So we'll do for n equals, which is the first one, the first block. Block number 1 is the super block. So let's go from n equals to 0, n is less than or equal to size n plus plus, and bm at n is true. And now we're done. Except for some possible troubleshooting. Got disconnected here. Did we get disconnected from Sociopath? Yes, that too. And the VPN. So we need to save this again. Maybe we did something to this as well. Oh. Bitmap declared as function returning an array. Right, so this is an array of booleans. No, wait a second. The block. Isn't block a block number? Okay. Did it like this. So where do I use that inside of the disk.c? Block. Block BL. Maybe I can maybe we can change it the other way around. So let's see. Where did we use block? We did not do it here. Here we do. Block BL. So let's just make this an int16 then. Same here. Okay, I guess that's it. Let's update our .h file accordingly. like so. Expected expression before disk. Let's write 13. This should be DD. DD undeclared. Well, I guess I mean FS. Has no member named inode blocks. Right, it's inside of the super. So fs meta metadata. Invalid type argument. Maybe we should have a dot here instead then. Expected blah blah blah. I is undeclared. This should be N. VM should be BM. This is a void function. Unknown type boot. Right, that should be a bool. Okay, now what? Conflicting types for FS format. DD, sector MBR, force. We have disk, boot sector, int 8, FS format. Disk, boot sector, bool. Open files, that's right, and busy. Let's create some empty functions for now. So what's the name of those? open files, close all files. And a close all files, disk dd, and this will just return. We need a signature as well. Let's mark these so we can remember that we need to take care of these later on. Unknown type name disk. Why don't we have access to that disk structure? Disk.h, disk.h. Maybe it's stupid to put those files, those functions inside of here. Let's do this instead. And let's go into our OSApi. Cut those out. H, we'll put them right here. Expected expression before boot sector 120. Right, this should be MBR. MBR. Well, I guess we need to cast this. Same with this. Right, reading 512 bytes from a region of size 34. IDX. Inode IDX. $128. Okay, so here we write one single inode. And we need to write the whole block. So let's create a block which is called IDX block. And we will zero out that thing. IDX block size. And then we want to copy into the IDX block the IDX and size of IDX. And now we can write the IDX block instead. And now it compiles. Nice. Let's also see if the command prompt compiles. All right. Nice. So when we come back from the break, we're gonna test this and see if it works as intended. See you in a bit. All right, welcome back, you guys. Before the break, we managed to basically finish the fs format function. But when I contemplated that function, I realized we made things a little bit too easy on us. I think the formatting of the actual disk is going to work pretty fine, but I don't think the bitmap is going to work fine, because we are indexed into this bitmap like this. But doing so, we will only grab at each byte, not at each bit. So we need to think this through a little bit more. So for now, let's focus on the actual formatting. So I will remove this part. Maybe we could remove all the way from here. So all of this. And for now, I will just set the bitmap to 0. What I want to do now is somehow to be able to test the formatting. So I'm going to create a formatting tool, a simple one. So I'm going to start by creating a new folder, which I'm going to call util. And I will create it here as well. And then I'm going to create a C file inside of the OSApi folder. We can call this dedos util.c. So I'm going to put this to the left here for easy access. And let's do the make file first. So this will be really simple. Only thing we're going to do is we're going to compile our diskutil.o from our diskutil.c, and we don't need its own H file for this, I think. And we're going to compile it basically the same way as everything else. And like so. And when we have this O file, we can create our diskutil, and it's going to take the diskutil.o, but it's also going to take the OSApi.so. So we're going to compile this by taking cc with the flags and possible C flags. And we take our input file. We provide our output file. And then when we are done, we move this file. So diskutil to our util folder, like so. And let's also add this to our all, so diskutil. So inside of here, we're going to include some things. I'm going to take stdio and all of those for now to make this a little bit simpler. And we're also going to use let's see how our fs.c looks like. This takes its own h, which in turn contain OSApi plus the features we need. So OSApi.h, and also this is gonna need disk.h, and it's gonna need fs.h. And let's define some functions. So usage, which is going to take int 8. Let's make it simple. This will take a char double star, and no, only one star. And we're gonna have an int main, which takes an int and a char double star. And I think that's all we need for this as far as function goes. So let's start with the usage, void usage, and it takes an arg. Let me just check one thing at the command prompt. If we do format/help, so -x is if we want to force a formatting. And is there a flag for creating a bootable thing? It used to. What if we do find boot? Maybe they dropped that in Windows 98 or something. So let's see. MS-DOS format command usage. This -s. That's good. So and then we need the drive number. Maybe I should name this usage format, because this util will take care of multiple different operations by the end. So this is usage format. Right, and we give it 2 copies of the arg. And then we exit -1. And then we have the main, and maybe we should create our format function as well. So void format, cmd format. And it's going to take up to 2 arguments. So let's do int a, no, char. Let's make our life simple, since this util will only be used in this this setting when we run the stuff on top of our own operating system. So I will also include string.h. So I can do something like, I need to put in the arguments. So int argc char argv. And let's do something like char arg1 and arg2. And if argc is less than 2, we will run the regular usage without the format thing. So we'll have that too. Usage char. And if argc is equal to 2, then we'll set arg1 equal to arg2 equal to 0. So that is if we have 1 argument. If we have 2, then we'll set arg1 to our argv1, arg2 to 0. And in all other cases, we'll set arg1 to argv1. And no, this should be arg. Wait a second. If this is equal to 2, that is one argument. So that's the command. Let's add that. So cmd. So in this case, we only have the cmd, then we set them to 0. Here we have one additional argument, so we set this to so, and otherwise we will set this to this will be 2, arg2 will be 3, and we will also set the command equal to 1. And if string compare command format would run command format and give arg1, arg2, else we'll just do usage argv, return 0, something like that. Not very elegant, but it's gonna work for us. So let's copy this, and again this will simply be usage and we're going to give a command and possible arguments. And the commands are at the moment only format. Something like this. And now we only need to take care of the formatting command itself. And it's going to take 2 arguments. First being, well, it depends, doesn't it? So let's just call them arg1 and arg2. And let's create so the first thing will either be the, what's it going to call it, bootable. And the second is the drive string. And if arg2 is 0, maybe we don't need to do it like this. Let's say we have an int 8 drive instead, and we have a bool bootable. So if we don't have a second argument, that means that bootable is false. And that we're going to select our drive based on this. So drive string will be equal to arg1 in that case. Otherwise, bootable will be decided by the first argument. So if arg1 is equal to this, and arg1 1 is equal to s, in that case bootable is true. Otherwise we show the usage. We don't have access to the arg0 anymore, so let's just say diskutil in this case. Let's also add a case if we don't even have an arg1. And then we'll go directly to the usage. Okay, so now I think we have everything. So we can switch based on our drive string, the first character of the drive string. In case this is C, we will set the drive equal to 1. And if it's D, drive is equal to 2. Break. And the default will be usage. Diskutil. Okay, so now we have everything that we need. And for now I will do, if bootable is true, I will print an error message. Bootable currently not supported. Exit -1. Okay. So let's also have a char force. Let's do something like this will format and erase your disk and disk number. Then we can make our lives easy by doing a scanf. Since we're only reading one character, I don't see a problem with it. So we can read this into force. Let's also have a boolean of force. Well, this is not the force, is it? Let's say it is. So our Boolean force will be equal to, if force is equal to small yes, or force is equal to big yes. In that case, B force will be true, otherwise false. And let's check the signature for our format function. So F is format, or it returns a file system. And takes in disk, boot sector, so we need to attach that disk. So we will run maybe first message, formatting disk. Yes. And we'll set dd. First we do init. What's it called? Disk init. And then dd is equal to d attach, which takes in a drive number. Otherwise, we're going to set fs equal to fs format. We provide the dd, the boot sector is 0. And the force is let's do this. So now we can give the force here, or the B force rather. And if we get an fs back, we will do an fs show. We haven't implemented this yet, but we will. But since it's not yet implemented, I will do this, and else formatting failed. And then we return. I think this is all we need. We need some variables though. We need to have a file system fs, and we need a disk dd. So let's see if this compiles. No rule to make target disk util.c. Didn't we provide that? Oh, I named it Theodos util. Let's link this to disk util.c. 13. went through but with warnings. Drive string is equal to arg1. Okay, 26 and 31. This was a weird error. Undefined reference to D attach. D attach. Maybe we can do something like this. If we put this variable outside and we make this public, but dd is a bad name because I use that all over. So now we should be able to include this thing. Extern public disk descriptor. Alright, so now we only should be able to call this disk init, and it should take care of most of the work for us. Let's undo that though. But let's instead set it equal to the first disk descriptor. Okay, let's try this again. Hidden symbol FS format isn't defined. Why is that a hidden symbol? Is it an internal function that too? Probably yes. Let's make this public. It's good to see that the public internal stuff works though. Okay, so now it went through. Drive. Didn't we use drive? Where is that? In disk-util, let's see. Drive. Right, we need to choose the disk descriptor based on let's do this. If we say that we can do drive -1 here, that will work, I think. And let's also go into our fs.c and temporarily remove this. Okay. Okay, it's linked to it like that. So let's do a copy of this OSApi library file, osapi.so, osapi.so. Now it should work. No? osapi.so not found. Let's compile this statically instead. No, not the O file. This one. It's not able to link that statically. Maybe we can link into the O files instead. So we'll do OSapi.o, disk.o, omni.std.o, and fs.o. Then we should get access to everything. All right, there we go. It's always a little bit scary to run this command. Okay, we did not get an error. That's a good thing, I think. Let's go into our drives and hex dump this disk. Okay, there's something there at least. So first a couple of zeros. So it's this number plus 1, 2. So echo 0x this plus 2, 498. Oh, it's 3 here, so 499 is this, 500. Well, let's do this instead. Okay, so 496 is this first 2-digit thing. 97, 98, 99. And then we have 2 reserved bytes. And then we have all Fs. So what is that? I need to look at my little sketch here. So that's the number of blocks. The first 2 Fs are the number of blocks. No, all of these are. Which means that we have 65,535 blocks, which is correct. How many inode blocks do we have? That should be this. So let's do dec of 0x this. 6,554. That sounds about right, because we're going to have around 10%. Then we have the number of inodes, which is 1. And then we have the magic number, DD05 and AA55, that's correct. And then the superblock is complete, so this is that. So the next thing is the first inode block. Okay, and the first field is the valid type field, 1 byte, B7. B7. Sounds a little bit weird, right? Well, this seems more valid. So a 3 is the valid type field, because that means that the valid is true and the type field is a directory. So that is what's expected. But what's this B7? What is B7? DEC0XB7 183. It's almost as if I missed 1 byte when I did this. And then we have a 44 over here. What's that? Well, we are getting closer at least. We have... we got most of it right. And the formatting itself is working pretty nicely. But we are probably off by 1 byte here. And this we need to figure out what it is as well. Otherwise, it looks pretty nice. So, yeah. Let's take a short break. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. All right, welcome back, you guys. I think I know what's wrong. I think we are off by 1 in our disk reading and writing macros. So instead of doing block size times these things, I want to do block size -1. And I think that's all we need. So let's go into our OSApi folder and make this project. And go into util and we run disk util format C:, yes. And now we go into the drives and we hex dump the disk. We still have this weird B7 thing and this 94, and this changes. If we run the formatting tool once again, format : yes. Now it's 84, but this stays as B7. And this time we did not get the 3-byte thing. Did I change the wrong one? Nope. Because we should get this this 3, since we are inside of our file system. We set this valid type to type directory, which is a 3. And before we had it here somewhere. Oh wait, here it is. Should we have gone the other way around, perhaps? Seems unlikely though, but let's try. What if we do block size +1? So now we have the 3, but we still have the B7, and now we wrote the B7 here. So we are writing the B7. Then it must be in one of our structures, right? So let's remove this code, because I think we had it right the first time. But where does that B7 come from? So it's right. Let's run this again, by the way. So we have the correct version. Okay, so here is the end of our boot sector and our super block. And then we have the B7. And then we have the 3. So if we look at our structure, our 3 comes from this, the valid type field. And size is 0, this is 0, this is 0, this is 0. And before our inode, we have our super block. And this is what it contains. So magic 1 and magic 2. And if we look at our definitions, it's DDO5, AA55. DDO5, AA55. But then this weird B7, where does it come from? And this 84, or whatever, it changes. Let's see what happens if we zero out our entire disk. So we go from dev 0 to disk 1, block size 512 bytes, count is 65,535. So now everything will be 0. So all we will be able to read from this disk will be stuff that we have written to it with our formatting tool. So let's run this again. And now we hex dump the disk. Same. We have this weird 74, which was 84 before. And we have the B7 right here. So if we were to look at this, this is B703, which means that first we have 3 and then we have B7. So it must be this size field. Let's try setting another size. What if the size was something like, I don't know, 0xEE? That should be easy to find. So let's reformat. And hex dump. Here is the EE. Which means that this is the size field. What if we were to set this to a 3 like this? Doesn't change anything. This is a really weird error. And what is this fs block type? Right, this is our union. And how do we write that union? It's here. And we zero out the entire FSB. What if we were to print the size of that FSB? Five, 4, 4. Why 5, 4, 4? It shouldn't be bigger than the block size. So a super block is this. Boot sector is 500. And then we have 1, 2, 3, 4, 5, 6 2-byte field, which is 12. So 500 plus 12. So the super block should be okay. Then we have 512 bytes. And we have pointers per block. That is 16 times the pointer. No, this is the right one. Pointers per block, what did I say? Yes, pointers per block. So 256 times the pointer, which is an int16, so 512 here as well. And the last one, we have inodes per block times inode. And inodes per block 16 times inode. So how big is that? It's this. So 2 plus 11, that's 13, 15, let's see, did I calculate this wrong somehow? Because it should be 32 total. And pointers per inode, that's 16. Wait a second. Pointers per inode. Oh, that's 8, I mean. So this is 16 bytes. And here we have, so these total should be 16. So this is 2, 4, 5 plus 11. That should be 16. Let's check all of these sizes. Because all of these should be the same. So we have super and we have data pointers inodes. So this is size of a super block. This is size of not sure how to write this. I guess int 8 times 256. And this will be size of pointers times pointers per block. And this is size of inode times inodes per block. Alright, let's see if we get a little bit wiser after this. Size of data 256. I think I did that wrong. Yeah, this should be times 512. But the problem is obviously the inodes. This is too big. Why is that? Maybe this is not. Maybe this aligns to 16 instead of 11. Do we need to say that this too is packed? Is that it? It says it's ignored. Hmm. 'Let's check what the size of a file name is. Eleven. But it must be this. What if we were to temporarily remove this? How much smaller will it be? We need to put something here. Let's put a single byte. Can we do that? Yes. So let's see what happens. So now it should be 10 bytes smaller. And it was 544 before, right? Yes. 384, that sounds like a lot less. 544 minus this. We need to account for that byte. 60 off. Well, what do we have? We have 2 int 8, that's 2 bytes, plus this 4 bytes, plus this 6 bytes. So if we remove that, we have 378. What am I missing here? Wait a second, we do have a inodes per block. So we have 256. Inodes per block. So inodes per block is 16. So it should be 16 times 32. That's what it should be. And if we remove the file name, that's 11 less. So 21, but then we have the additional byte. So this is what we should have. So we have one too many inodes. It's weird. What are we supposed to do? This, but I don't see that making sense. Still doesn't change. Oh, the inodes shouldn't change. Okay, so FSB, what did it have before? Okay, so it was 544 before. If we take this divided by 16, we get 34. But how many are there? So this is inodes per block. Inodes per block is 16. And am I printing the right thing? Inodes per block. So how big is a single inode? $34, and it should be 32. Pointers per inode, that's 8. So this is 16 bytes. And this is 2, 4, and 5. And if we remove this, how much is a single inode? $24. So it decreased by 10, and we added 1 plus 1. So the file name is 11. Wait a second. We have this 2, 4, 5. No file. Let's check how big this is, the direct. That should be 16 bytes. So can we do size of, let's see, index dot direct. It is 16. Uh, 24. How did we define IDX? That's an inode. So let's see. What do we have here? The direct pointers are 16. The indirect is 2. The size is 2. The valid type is 1. What about the file name? Where did it go? Size of name 1. Maybe we need to do make clean. Size of name 1. Didn't I save this? Okay, so name 11 and 16, 2, 2, 1. And this becomes 34. So we have 11 plus 16 plus 2 plus 2 plus 1. That's 32 in my book. What if I move this here? Okay, so that's it. I have the pact in the wrong place. It should be here. It's weird that it doesn't warn about that. Let's see if we use this somewhere else. Here we do. Okay, I think we got them all. Okay, so now that's okay. What happens to the disk? Okay, now it looks better. So that was the error. Really tricky one. GCC warns for all kinds of places that we put our attributes, but not when we put them there. So now we may, where is it? We may set the size back to 0, where it should be. And this should be type directory, like so. Alright, so if we run this again now, we should have a correctly formatted disk, and we do. Look at this. And everything else 0 as intended. Oh, that's pretty great. Alright, so now that this is done, what's the next step? We need to fix our bitmap, because the problem was with this code, I was parsing it as a 8-bit thing. So byte by byte. And we can't do that. We need to create some bitwise functions. So let's put them inside of OmniSTD. I'm gonna have 2 macros and 2, and 2 functions, I think. So something like internal bool, and this will be called getBit, and it takes a memory address to a character, or a int8, and it takes another int8 which specifies which bit we are interested in. Now let's make this an int16. So we want to be able to get a bit out of a larger string, a string of booleans. And we want to be able to set a bit as well. So we'll have an internal void set bit. It too takes an int8 string. I think. Yes. And it takes in what the bit position and what value, so I need a bool as well. Alright, so these will take care of a larger string, but I want a macro which handles a single byte. So let's call this, maybe we should define it here. So let's say this is the get bit prime. And in a specific byte, that's B, we want to get a specific position. which is P. And how do we do this? So let's say we have something like 1101 0011. This is our byte. And we want to get this. So the 5th bit. So if we index from 0, this would be bit number 4. So B is equal to this, and P is equal to 4. So first we need to mask it. So if we take a 1 and we shift it over P positions, so if P is 0, we don't shift it. But P is 4 in this case. So we start here and we move this, let's put them like this, and we move it so we shift it 4 positions. 1, 2, 3, 4. No, it's right. 1, 2, 3, 4. So that this is the correct one. So now we have a mask which looks like this. 0, 0, 0, 1, 0, 0, 0. That's our mask. Now we want to AND this with a byte. We take the byte and we AND it with this. Which means we turn this string into our mask in this case, since this matches. And now we need to shift it back. So we need to make this, so this is 1, 2, 3, 4. Well, we need to shift it back 4. So we have this, and we shift it back P positions. And this is our macro. It looks like, I don't know, Greek or something. So how do we set the bit? Set bit prime will take in a byte and a position and a value. So let's say we want to set the same bit. Which means P is 4, B is this, let's say, and the value is 0. So we want to set it to 0. So this time we want to create a mask which looks like let's see. Let's start by creating a mask same as we did before. So we take a 1 and shift it over P positions. So now we have a mask that looks like 0, 0, 0, 1, 0, 0, 0, 0. Well, let's say we want to set it to 1. So now we have this. And now we want to invert this. So instead we have 1, 1, 1, 0, 1, 1, 1, 1. So let's invert this whole thing. And now we want to well, basically this will be unset bit. So let's remove this value. And then we can just take the byte and AND it with this. That will unset that bit. And if we want to set that bit, take a B and a P. Start with the same thing, 1 shifted over P positions. So now we have the mask that we had before, and in this case we will just take the B and we will OR it with this. And that is our macros, I think. So how do we test this out? I guess the easiest way would be just to go into the formatting tool. Let's say we have a byte B. No, int8 byte B. And we have a bool x. b is equal to 0, x is equal to 0, false. And we want to set, let's say, bit number 3. So that's index 2. So our byte will be equal to set bit prime, and we give it the byte, and we want to set this bit. So what should be the result? We have this from the beginning. We set third bit, that's this. So this is 1, 2, it should be 4, right? And let's do it one more time. But this time we will set bit number 0, which should make it 5 the second time. Alright. Byte undeclared. Right, we call it B. It works. Pretty nice. And let's see if we were to unset bit number 2 again. So this time it should be 0 the second time. Okay, that works. And let's see if we can get the byte. So before we remove it, we want to set our x equal to the bool of get bit prime of b at position 2. And this should be true. And then we do the same after we have unset it. So the first time it should be true, the second time it should be false. Yes. Okay, so our macro works perfect. And it's quite beautiful, right? But now we need to create those functions that handle a large string of booleans. Right, so let's start with this get bit. So it's an internal boolean get bit, and it takes an int 8. I don't know what to call it, string, and it takes an index, so int 16 idx. So inside of this large string of booleans, so basically of bits, we want to grab at a specific one. So let's do int 16 blocks and mod, or maybe we could do int 8 mod. So blocks should be equal to the index divided by 8. That's how many blocks forward we want to go. So we want to skip this many to get at the right position. And when we get there, we want to move idx mod 8 steps further. Because every byte consists of 8 bits. So if we want to go, let's say 500 bits forward, we take 500 divided by 8, and then we get pretty close. And to get the last couple of steps, if this is not divisible by 8, then we can move a couple of additional steps. So let's define a void mem where the mem is equal to the void of the string plus blocks byte let's start there. And let's create an int 8 byte. So the byte is equal to the mem. The mem position. And now we want to get specific bit from, is it this block or the next one? I think it is this one, right? So let's say we have this. And we want to go to this bit. And let's say these are bytes, by the way. So blocks is equal to x divided by 4. I'm going to go to this. Well, I think we're at the right place. We'll see, won't we? So the bit should be equal to the bool of get bit prime. And we need to provide this with a byte, so we do this. And the position should be the modulus, which is somewhere between 0 and 7. And then we return that bit. I think this should work. And I think the other function will be rather similar, so let's do a copy of this. Only this will be a void, and it's set bit. Takes in a string, an index, and a value, right? Bool val. So if bool is true, we want to do set bit prime. Of the byte at position mod. Otherwise, we want to do unset bit prime of the same thing. Something like this. So let's use these functions in our code. So we read through the inode blocks. And we read through each of these inodes. And instead of doing this, we do set bit of the int 8 of bm at index, and the value should be true. And same here, only false. Okay, I think this is good. And bitmap alloc, we iterate through the blocks, and if bm at n, this should be if get bit of bm at n. And we should set it to true. So we'll do set bit of bm at n true. Right? And this bitmap free, bmn is equal to false. So this should be set bit bm at n to false. Okay, that should work. And how do we use this? Okay. So we can keep this as is, only changing this part to set bit b of bm at position n to true. Remove this. All right, I think we're done. We do, however, need some way of printing this result. Let's do something like this. So the bitmap is equal to and we do a for loop from 0 to dd blocks. And at each position, if get bit of the bitmap at position n is true, and we print 1, else print 0. Let's also divide it a little bit. So if n mod 8, let's say, so every 8th bit we print a space. All right, let's see if this works. No. Define bool int 8. What's that? 3. I think I did something wrong in my code. Let's check 57 and 59. 59. Wait, if bool if val, this is what it should be. BM undeclared 153. Right, we removed that. So let's put it back. All right, it compiles at least. B and X are unused. Never mind that. So let's go here. Let's format this thing. Okay, so this is our bitmap, 0, 0 everywhere. Well, it goes outside the screen. That's a little bit weird. Let's say if n is divisible by 64, then we'll print a new line. Let's also check if n is more than 0. Alright, let's see what happens. Still goes out the screen. Maybe we should have if here and not else if. Alright, that's better. So there's a lot of zeros. At least a couple of these should be ones in the beginning, I think. So one super block, one directory. But the directory is not occupying any block, is it? Only the inode blocks, and this accounts for that. So let's remove this. But this should be a couple at least. And we set those bits, or we try to. Maybe I'm using this wrong. I measure to byte is equal to this. Let's not print all of them. Let's only print like 100 or so. All right. Fingers crossed. Well, it should be quite a lot of blocks actually, because 10% are inode blocks. Maybe we should use this one. Let's do this. We get a little bit of separation. Alright, so we have a lot of ones here. And these are all the inode blocks because they shall be occupied. And then the rest, 90%, should be zeros. Alright, it works. We can cross this and this and this. Yeah. So now we have a working disk formatter. The next thing will be to create a simple show function, which will just print information about the disk. Shouldn't be a problem. And then we can start creating the mounting functions. Now that we have a formatting function that works, we are going to take care of the mounting and the unmounting, and also this show function. I think we're going to start with this show function. So we can just print some information about the operating system. So let's go into fs.h and create an internal void function, fs show, and it's going to take a file system and it's going to take a boolean. So the boolean will decide if we are going to just print info about the file system or if we are also going to print this, so the bitmap. Right. So this shouldn't be too hard, I think, but we'll see. So internal void fs show, taking a file system fs, and we take a boolean show bitmap. Right, so if we don't have a file system, we can early return and print nothing. So let's start by printing some stuff from the superblock. Let's take a copy of the inode. Well, let's take all of these. So we'll create a comment and paste it in and reposition this a little bit. So let's begin with this one. So let's see. Let's do drive and then the C colon, for example. Maybe we should do disk and the number 0x.02 HHX mounted on something like this. So the first is going to be a char version of the drive number. So we go to fs drive. And let's create a int8 which maps this drive number. Didn't we have a function for that? Maybe not. Well. So what are we going to call this? Drive char. I don't know. So the drive char will be equal to if the fs drive is equal to 1, will be equal to C. If the fs drive is equal to 2, this will be D, and otherwise question mark, let's say. I think we need to cast these to int8s. Alright, so what else are we going to print? Not much from this, except for the bitmap, which we'll do a little bit later. The super block, on the other hand, contains a lot of interesting info. Let's see, does the drive structure contain anything we want to show? No, not really. Okay, so let's start with the number of blocks. Percentage blocks, total blocks, and this number amount of inode blocks. Containing this number amount of inodes. So we have the fs, and this should be an integer. Fs blocks and fs inode blocks and fs inodes. Alright, so that's all we need from the super block, and now we should iterate through all the different inodes. Maybe we should create a function which returns a specific inode. We will need that later on, so why not now? So this will return an inode star, and let's call it find inode, and it takes a file system and an inode number. int16 then. Or a pointer rather. So internal inode star find inode file system fs and pointer. What should we call this? Index. So what do we need? We need a block BL so we can read in. And we need a couple of int16, let's say x and y. So we first need to have a loop. Let's also have an n, by the way. So we need to have a loop where we go through every inode block. So let's set n to 0, and we set x equal to 1. That's the first, or 2 rather, because number 2 is the first inode block. And we're going to iterate as long as x is less than fs metadata inode blocks. But this is the total number of inode blocks. So if we only have one, we want to iterate once at least. So as long as x is less than inode blocks plus 1, I guess. Or less than or equal to inode blocks plus 1, x plus plus. So first we zero out our block. Then we do fs read and no, d read. And we need to have a disk, so it's fsdd, and an address which is, let's see, should be the block like so, and then the block number, which is x. Also create something for the return value. And if it's false, we can probably return. Otherwise, we have a block full of inodes, which we need to iterate through as well. So we'll do another for loop where we set y equal to 0 as long as y is less than inodes per block, y plus plus. So we want to check first of all if this is valid or not. So let's see, how do we do that? Maybe we should take this in steps. Let's create an inode. Can I name it the same? I'm not sure. So the inode is equal to what exactly? We have something called fs block, don't we? It's better to use this one. Fs block. So let's make this block an fs block instead. And when we read into it, we can go to the block.data. And then we don't need to create this inode. We can just reference that part of our block, I guess. So something like if the bl dot inodes at index y we want to take its valid type we want to end it with 1 and then we will have either true or false if it's valid or not. If it's valid, we want to print some stuff from it. No, we want to return the inode, right? So let's call this res instead. So I can create an inode star, which is the return value. Let's see. Now we need to change this a little bit. We still want to iterate through this, but every time we do, we want to increase a counter. Let's say int16 counter. We haven't used n though, have we? So let's use that. So every time we go through a block, we want to increase n, but not quite yet. Let's do it here instead. So if n is equal to the index that we are looking for, then we have found our return value. So let's set this to what exactly? Well, we want to set it to the block dot inodes at index y. Actually, we should probably make a copy of this thing. Let's set this ret to inode star 0 from the beginning. And when we find the right thing, we want to do an allocation. So we need a size. Size size is equal to size of struct s inode ret is equal to inode star alloc size. If we don't have a ret, we can early return. Otherwise, we first zero out this thing. And then we copy into our ret from our block dot inodes at y well, the whole thing size. Break. And that's basically all we need to do, I guess. And if we are done with the loop and we haven't gotten a result, we can just return ret anyway, because it's 0 or it has worked. This should be down here. All right, I think this is gonna work. And let's define like this. Then we do pointer xy instead. That's more accurate. Okay, so now we can locate a specific inode. So now we can just iterate through all the possible inodes. So we'll have a pointer inode number. So inode number is 0, and as long as inode number is less than the file system metadata inodes, inode number plus plus. Then we can set the inode equal to find inode, We give the fs and the inode number. And if this is not there, we can break. Otherwise, we'll print some info from it. So inode this. So valid type. Well, if it's not valid, we don't want to print it, I guess. That's right. So if we take the inode valid type and end it with a 1, this is true, then we want to print something. And size in bytes. I think that's enough for now. So the first is just the inode number. Then we have the type. So if inode valid type is equal to type file. Then we say it's a file. Otherwise we check if inode valid type is equal to type directory, then it's a directory. And otherwise unknown, let's say. Then we have the file name. So let's first check if the inode number is equal to 0. Then we want to return slash. And otherwise we want to take the actual file name. So let's say we have a function which is file to string, and it's going to take our inode name. And finally we have the size, which is just the integer of inode size. I think we got everything. Okay, so we need to create that file to string because the file name is in this format. So let's say we have an internal int8 file to string, and it will take a, is it file name? Yes. So file name star, let's say. So internal int8 file to string takes a file name fname we can do static int8 buff 16. If we don't have an fname, we will return 0 like this. Let's also create a pointer int8 ret. And we need to have some int16n as well. So let's start by zeroing out our buffer. And now we copy the first part of the file name into the buffer. So we do a string copy. And the destination is buff. Source is the fname name. And we copy most 8 bytes. And now we need to know the size of this thing. So n is equal to stringlen of buff. So let's say we have the name equal to config, extension equal to sys. So now our buff will contain config, and n will be equal to 6. So the indices is 0, 1, 2, 3, 4, 5. So at position 6, we want to put in a dot. So let's increase this n. And we index into buff at n and set it to a dot. And maybe we should name this P instead. Then we can increase this n again. Maybe we can do this. And to this position we want to copy the extension. So our P will be equal to buff plus n. And now we do a string copy into P from fname extension and maximum 3. And we set p equal to buff and we return buff. No, we return p. Think this is going to work. So now we should get this in a nice format. By the way, if we don't have an extension, if the extension is 0, so if fname extension, if we index into this thing, and if it's 0, so if the first byte is 0, then we can just return fname name. So without any dot and without anything other. That's good. Okay. I think we have our show function. Now we only need to troubleshoot, but I guess it should be fairly straightforward. Um, 20 and 21 is unused. Let's just check that real quick. Right, this is old stuff. Uh, 198. Incompatible type for argument 1 of file to string. $2.19. Well, maybe it wants the address like this. $2.74. String copy buff. Fname name. File system has no member named blocks. Right. This should be fs metadata.blocks. Fs metadata.inode blocks. Fs metadata.inodes. Pointer type mismatch in conditional expression 219. If inode number maybe it's this one, so this should be a char. Cannot convert to pointer type 241. Return with no value 244. Implicit declaration of string len. Where did we put string len? Is it in omni? std perhaps? String len. OSApi perhaps? So many functions. Yes. Let's move this to this place and make it internal instead. And let's see, need to take the C part as well. Into here somewhere. And it should be internal. Alright, let's try that. One oh two, 103. Okay, so how do we test this? We can put something into our We don't have a mounting function yet, so we can put it inside of our disk util. So when we have formatted, we can print the information. So let's put it inside of the formatting function at the end, temporarily. We forgot one thing, this bitmap thing. So if bitmap, what did we call it? Show bitmap. So then we do all of this. And we need to get the, let's see, this will be FSDD blocks. We need to have the VM. So this will be FS bitmap. Yeah, I think that's it. N undeclared. Alright, let's go into our disk util. We do format C colon, yes. I forgot to add that part. So this is the formatting function. So let's do fs show of fs false. Okay, so disk 1 mounted on C colon, 65,535 total blocks, 1 super block, blah blah blah, inode blocks containing 1 inode. But we didn't print that inode. So for inode number equals 0, while inode number is less than inodes, inode number plus plus. So it's probably our find inode that fails, and we give that a 0. And it's 0. X is 2. As long as x is less than or equal to inode blocks plus 1. Maybe we can do an S-trace and see what we get from that. Well, we read in a lot of blocks. That's expected. Illegal seek. We go very far. And the last thing we try to read is at this position. So if we take this and divide it by the block size, okay, we're probably only off by 1 or so. So let's change this to less than. Mm. Same thing. Is it the same values? $65, $53. And how many inode blocks did we have? $65, $54. Maybe we shouldn't have this plus here then. Okay, so now we go to this. Let's do an L trace and see what that says. What is this put char? Is it this printf that does that somehow? So inode%t type %s. This is the inode number. If value type is type file, then we return file. Otherwise, we check if it's type directory. Print directory. Otherwise, print unknown. If inode number is 0, print this as a file name. Otherwise, this. So let's see what it says. Found inode 0 at the address blah blah blah, not valid. So it does not think our first inode is valid. Even though we have this type. So if we do a hex dump on our drive, so this is our inode. I think it should be valid. Let's temporarily remove this if statement. And let's see what happens without. Inode 0 is valid, type unknown. And why does it loop so many times? It should find this immediately, right? But maybe that has to do with the formatting. So let's check the valid type field at this point. Perhaps something messes up when we copy it or something. No, this loops a number of times. Here it's the correct one, but it continues to loop without increasing this number. Wait a second. We break out of this loop, but not both. Huh. Maybe we should do something like, we can set x equal to -1. Then we should be okay. Now I think it's going to work. That's more like it. Found inode 0 at this address. Inode 0 is valid. Directory. File name is this. 0 size in bytes. Maybe we should just say name and not file name, since directories are there as well. Alright, that's great. So let's also try to show the bitmap. And that should work because we have already tried basically the same code, but just to make sure. And it's a lot of zeros with a couple of ones at the top. That's nice. So now we have a show function, ladies and gentlemen. And after the break, we will take care of the mount and unmount, which I think will go rather smooth. I'll see you right after this. Alright, welcome back you guys. So before the break we managed to create an fsShow function. Now we're gonna focus on the mounting and the unmounting. And I hope that will be rather simple since we have written most of that code already. So let's see. This will be two internal functions. So we are going to have one fsMount, which is going to take in a file system pointer. No, it will not. It's going to return a file system pointer. It's going to take in a well, I guess the drive number. So an int8 drive number. That should be all that it needs. Then we'll have an internal void function, because this shouldn't fail. And this will be the fsunmount, and this is going to take in a file system pointer. Alright, so in order to mount a file system, we need to fill in this file system structure, basically. So let's do that. I will make a copy of this one. We'll go to the bottom here and paste it in as a comment. So we have it easily available. So this will be an internal file system fsMount, and we'll have an int8 drive. So first we need to check well, we need a int8 index, or maybe we can make it so we can reuse it. And the index will be equal to the drive number -1, and this will be the index into our global file descriptor structure. So let's make our lives a little bit easier and define a disk dd like so, which will be equal to the global disk descriptor of index. And if we don't have a dd, this operation will fail. So let me see. Well, let's do it like this for now, just returning a 0. If we decide to make this a part of our public API, which we probably will, or some version of it, then we need to take care of different return values, error messages. but not right now. Alright, so let's see. We should also check if this is already mounted. So maybe we can do it like we did with the disk descriptors, that we create a public variable, which is an array of pointers. So this will be public file system fs descriptor. And we're gonna have maybe we should define a constant which is max drives, max drive. So this we can put inside of disk.h, I guess. Maybe I should close down a couple of these. Because I'm not going to use all of them all the time. So OSApi and this. It will be a little bit easier to find our stuff. Alright, so let's define a constant. So our max drive will be 2. And inside of our disk initialization function, which is called dinit, instead of doing it hard-coded like this, let's create an int 8n, and we do a simple loop where we loop from n to from 1 to or equal to max drive n++, and for each one we will do disk descriptor plus n is equal to d attach of n. We'll do a similar loop for the unmounting. So detach disk descriptor of n. Like so. And those disk descriptors, now we can use our constant here instead, max drive. Makes our code a little bit more manageable. So now we can begin mounting our file system. And let's start by allocating room for our structure. So let's define a size. And the size will be equal to the size of a struct as file system. We'll set fs equal to a loc of size. And if this fails, we fail. Maybe before we index into this thing, perhaps we should check that it's not bigger than max drive. So if the drive is bigger than max drive, we fail. And if we do get memory for this, we want to zero it out. And start filling in the different things. So, the fs drive number will be equal to our drive number. Our fs dd will be equal to dd. Our fs bitmap should be equal to make bitmap. We give it our file system and we want to scan. We haven't tried that scanning function yet. I don't think we have. So that'll be interesting. And then the super block, that one we need to read from the disk. However, it seems a little bit well, it's not very optimized, but who cares about that? It's about, maybe 500 bytes of memory. It's not too much. So let's create a fs block which we will zero out. And we do a disk read. We give it the disk descriptor, so the fsdd. We give it an address. So this will be, well, it's going to be the block, right? So I don't remember if we need to cast this, but let's not. So this will be the address of our block, and the block we want to read is the first. And if this fail, we fail. In that case, we need to free the memory and return an error. Maybe we could actually read this directly into our structure. So into our fs metadata. Well, we don't need to zero it now. So fs metadata, and then we don't need this fs block. We should also check if this fs bitmap failed. If we don't have an fs bitmap, we will destroy our file system and return an error, because we don't have any good way of keeping track of used and unused blocks. So we don't want to mount this file system in that case. And that's it. So let's log to some kernel log somewhere that we have mounted this thing. So let's do kprintf. I haven't defined this yet, but we want to say something along the lines of mounted disk 0x % x on drive %c : and the first thing will be the drive number, and the second, let's do the same ternary. So if drive is equal to 1, we want to return the character C. drive is equal to 2. We want to return D, and otherwise a question mark. Let's put this kprintf inside of omni_std.h. And for now, all we want to define this as, so kprintf, we have a format string and we have args. And let's just run a printf for now, where we take the format string and we add a new line. And then provide for the args. So this means that our kprintf will need to have at least one argument. Otherwise, this will end with a comma, which is no good. Later on, we will let this print into a buffer, which during the boot will print to the standard output, to the screen. And after the boot is complete, it will write to some file perhaps, or some buffer somewhere, which you can read using some log function. That's the general idea. Alright, so before we return, we want to put this inside of our fs descriptor global variable. So, did we change this index? Nope. And we can use it like this. So our fs descriptor at index should be equal to our fs, and we return the fs. So this is our mount function. Pretty simple. And the unmount should be even more simple. So internal void fs unmount file system fs. If we don't have an fs, we just return. We'll set our index equal to the fsdd drive -1. We'll set our global fs descriptor at index to 0. We will free our fs. We will return. maybe we need to do a kprintf as well. So kprintf unmounted. Let's do this. int16 drive. Drive equal to fsdd drive. And this should be equal to drive -1. And now we can just copy this thing. We'll just say unmounted drive and the drive number. I mean the drive. We need to have some namings that's not conflicting. Let's say disk number and drive name or something. I don't know. Okay. So when we have initialized our disks, maybe we should mount at least the system drive. So if we have disk descriptor plus n, then we want to fs mount and let's include this first. It will be a little bit of round. Well, let's try it. We include fs.h. So we fs mount our our C :drive. Guess we can just do this. Plus n is not very good though. This should be plus n minus 1. Okay, will this compile? Unknown type disk. $36. Okay, so all of a sudden this is a problem, and this is probably because we are going in a round robin kind of way with the includes. Let's see if this error disappears if we remove this. Yes. Okay. Well, first of all, we can fix this error at line 30. This should be a disk descriptor with a K, nothing else. And we will probably not be calling the fs mount later on, so maybe we can do some kind of hackish solution to this. If we go into the fs.h and we just copy this signature, put it above, I guess we should be okay. Fs mount, fs mount. Oh, wrong file. This should be disk.c. Well, since this will be removed later on, let's copy this stuff too. One thing will require the next thing, and so on and so forth. So we're gonna need the boot sector as well then. And we need the superblock structure, and then I think we're done. A lot of noise. Okay. Okay, maybe we shouldn't put that inside of a parenthesis. It's better. Disk descriptor is undeclared in fs.c. Is it? Haven't we used that before in this file? Disk descriptor. fs. No, maybe we haven't. Well, that's easy enough to fix. So disk descriptor, we will just copy this thing. This should be an extern. And now I think this will compile. Yes, it does. Will it work though? So how do we test this? Maybe we can just run the command prompt. Mount the disk on drive C, colon. That looks good. So now we can check those off. All right. We are halfway there. Yeah, that's good enough for one episode, I think. If you like this episode, please like and subscribe. And thanks for watching. Thanks for today.